divergence of a tensor. Okay, divergence of a tensor, let's put divergence of a vector. This is partial of v1 respect to x1 plus partial of v2 respect to x2 plus partial of v3 respect to x3. Now, in Cartesian tensor notation, you just write down partial of vi respect to xi, or vi comma I, as you saw. Now we can show this just clearly because, okay, nabla, you see nabla is E1 partial respect to x1 plus E2 partial derivative respect to x2 plus E3 partial respect to x3. Now this dot v, you see, this is v. So v1 e1 plus v2 e2 plus v3 e3. So this is equal, see, e1 dot e1 is 1. So here is partial of v1 respect to x1. e1 dot e2 is 0. e1 dot e3 is also 0. So plus now e2 dot e1 is 0. e2 dot e2 is 1. So this is partial derivative of v2 respect to x2, and e2 dot e3 dot is also 0. Now e3 dot e1 is 0, e3 dot e2 is 0, so e3 dot e3 is 1 plus partial v3 respect x3. So this is equal to the divergence of a vector. Attention now, this is a scalar. A scalar, see? Divergence of a vector, you see, decreases by 1 the order of this vector. Let V be gradient of phi. So the divergence of gradient of phi is equal, now this is nabla, you see this is nabla over here, and this is a vector nabla phi, this is partial of phi respect to x1 plus partial phi respect to x2 plus partial phi respect to x3. You see it's the same, so this is equal partial respect to x1. Now this here behaves like v1, this is v2, and this is v3, like we did before. So the partial v1 respect to x1 plus partial v2 respect to x2 plus partial of v3 respect to x3. This is equal partial respect to x1 of v1, you see, is partial phi respect to x1 plus v2 is partial respect to x2 of partial phi respect to x2 plus partial respect to x3 of v3. You see v3, this is partial phi respect to x3. So this is a second derivative, second partial derivative. So this is partial of phi respect to x1 squared plus partial derivative is second derivative plus partial of phi respect to x3. This is the same, okay? Look, nabla phi, we can just put like this. See? this is called Laplacian. Laplacian of phi. See? This is called Laplacian. Laplace is just... Now, how we represent the Laplacian? So, you see, this is equal here, the Laplacian of phi. Now just put this. You see, this is a scalar. Okay, this is a scalar. Just put phi dot, in this case, I. Or phi dot j. Or, you see, that's it. These are dummy indices. See? Because this is a scalar. This is a scalar. Okay. Rotational of a vector. Okay, now we are doing a representation of gradient, divergence, and rotational in the Cartesian notation, see? Cartesian coordinate notation. That's why we repeat here rotational of a vector. Let's put a vector v. We did this before, so the rotational of v, you see, you have the determinant. Let's put E1, E2, E3. Now, here the components of this pseudo vector over here, partial respect to x1, partial respect to x2, and partial derivative respect to x3. And now the components will be v1, v2, and v3. Now, this is equal. Now, you see the determinant here, okay, will be E1. Now, partial v3 respect to x2, partial of v3 respect to x2, minus, you see, minus partial v2 respect to x3. Partial of v2 respect to x3, this is E1. Plus, as I said before, this is cyclic. After 3 is 1, after 2 is 3, you see, E1 will be E2. So I will just put over here, see, now partial of V1 with respect to x3 minus partial of V3 with respect to x1. Now, after E2 comes, after E1 comes E2, plus, now, after 1 comes V2, x3, x1, minus, now, after V3 is V1, and this x2, after E2 comes E3. Now, how we represent using the permutation symbol. Now, you see, look, rotation of V, now you'll be using the permutation tensor. Now, here will be epsilon I, j, k. Now, here you have to be careful, partial of Vk respect to xj. Attention on here, attention this. Let's see for I is equal 1. Okay, we must reproduce this component over here. Let's make I is equal 1. Write down here, I is equal 1. Okay? I is equal 1. This will be epsilon 1 jk partial of vk xj. This is equal. You see, now J is dummy and K is dummy. So let's add and J. Okay, here J is equal 1. This will be 0 because epsilon 1, 1 is 0. So that's J is equal to 2. So epsilon 1, now 2K partial of VK x2. You see, because J is 2 plus epsilon 1, this case it will be 1, 1, 1. It can't be 1 here. J2 is here. Now J3, 1, in this case 2. Let's put 3 here. Okay, 3 K partial of VK with respect to x3. You see, look, what I'm doing, I'm summing only on J. Remain K fixed. Now, this is, okay, J cannot be 1 because epsilon 1, 1 is 0. So let's start J from 2. So 2 here, plus 3 and 3. Now, look, K here cannot be 2, neither 1, because epsilon 1, 2, 1 is 0, epsilon 1, 2, 2 is 0. Okay, K here must be, in this case, must be 3, because K is equal 1, epsilon 1, 2, 1 is 0, K is equal to epsilon 1, 2, 2 is 0. So here K must be 3. So this is equal epsilon 1, 2, 3 partial of V3 with respect to x2. See? Now, on this term over here, K cannot be 1, K cannot be 3, because if K is 1, epsilon 1, 3, 1 is 0. If K is 3, epsilon 1, 3, 3 is 0. So K must be 2 over here. So this plus epsilon 1, 3, 2 partial of V2, see K is 2, partial x3. Now, partial of V2 with respect to x3. So this is for I is equal 1. Now, you see, epsilon I jk, attention here, partial derivative of Vk, this case, Vk of xj. Never forget this. This is rotational of V, written using a Cartesian coordinate. Now, what is important here, okay, look, I put here K comes here, and this is J, and J comes over here. That's important for you to see. Don't confuse on this, okay? You always do like that. So, it's a brief review. Number gradient of phi is phi comma I is the same as partial of phi respect to xi. This is a vector. Now, divergence of v is vi comma I is the same as a summation. This is xi. So this is dummy, so it can sum. Now, rotational of v is just we did right now. We did this just minutes before. Now, just for you to remember, A cross B is F I J K. You see, J over here and K over there. Okay? This is the same if I exchange this J K I over here. Okay? It's A J B K. The same. Okay? This is J. Put JK over here. J and J So this is K, and K. The same. See? This is equal. Because here, you see, I remove once and twice. So you see, it's minus once. Again, minus is plus. So this is equal to that one. And this gradient of V we already did the last lecture. So this is a second order tensor. See, there's a second order tensor here. See, there's a second order tensor. Second order tensor. Gradient of a vector, which is first order tensor, increased by 1. Now, don't forget that. If you want the matrix, don't forget partial Vi, I is column, with respect to xj, G is a row. Okay? Now I will develop the divergence of a second order tensor. For sure, this will be a vector. Okay? Because divergence decreased by 1 the tensor order. Okay? Now you see nabla, it's nabla over here. You see nabla dot, you see dot. This is a second order tensor. This E1, E2, and so on. Now let's do the dot product. You see this here, let's close here. Okay? I will erase here and I'll continue on this left part of the board. Now, let's see. So, this is E1 dot, this E1 over here, E1 over here, E1 over there. So, this first term, when applied to that will be 0. Because you see E1 dot E2 is 0, E1 dot E2 is 0, E1 dot E3 will be 0. So develop this first over here, we'll have E1 dot E1, this will be partial respect to x1, you see, A11 would be A11, E1. You see, look, these apply to that. U1 dot U1 will be 1. So it's partial of A1, E1. It's over here. Plus, now, this one dot this one. So E1 dot E1 will be 1, so it was left E2. So there's a partial respect to x1, partial respect to x1, you see this here, of A12, E2. I'll repeat again. U1 dot this one, U1 dot U1 will be 1. So it was left E2, you see? So partial respect to x1 or A12, E2 here. Plus, now the last one, U1 dot U1 will be 1. So in the left E3, or say this first, the third one here will be partial of A13, 13, with respect to x1, E3. See? Now, I'll repeat. U1 dot E2 will be 0, U1 dot E2 will be 0, so this will be 0, U1 dot E3, you see E3 comes first, so it will be 0. Now let's develop this. Now, E2 dot, you see, this always U1, so E2 dot this whole term here, 1, 2, 3, will be 0. Now, E2 dot E2, it will be 1. Now, E2 dot this whole terms over here, these three terms, E2 dot this three terms will be 0. Because E2 dot E3 is 0, E2 dot E3 is 0, E2 dot E3 is 0. So, only the only difference from 0 will be these three terms over here. So E2 dot E2 will be 1, which was left U1. So this is a partial of A to 1 respect to X2, partial of A to 1 respect to X2. What was left? U1. See? Just you do this carefully and there is no mistake. Now, E2 dot E2 will be 1. So partial of A2 2 with respect to X2, E2. Partial of A to 2 with respect to X2, E2. Plus, now, E2 dot E2 over here will be 1. So it will be partial of A2 3 with respect to X2, E3. Partial of A2 3 with respect to X2, E3. You see? Now you can see from here, you see, just this one we can write just easily. Just see the sequence here. But let's do it. Okay, E3 dot E1 is 0, dot E1 is 0, dot E1 is 0. E3 dot E2 is 0, E2 is 0, E2 is 0. So E3 dot E3. So this partial of A31 with respect to X3, partial A31 with respect to X3. What was left? U1. Plus, now, E3 dot E3 will be 1. So partial of A32 with respect to X3, partial A32 with respect to X3, E2. See, E3 dot this one. E3 dot E3 is 1, so it will be partial respect to X3, A32. Plus, the last one, E3 dot E3 is 1, so partial respect to X3, A33. Partial respect to X3, A33, E3. You see? Now, here comes the vector. Let's put here, so U1 over here. Let's find out U1 over here and U1 over here. So this is equal, now, partial of A11 X1 plus partial of A21 respect to X2 plus partial of A31 respect to X3 E1. See? Now, this one, it's here. There's a vector, you see, plus. Now, this is cycling. I could write down here, just look in here. So, I will raise it here and continue there. So, let's do it. Okay. Let's do here. Plus, you see, it will be plus here. Now, let's find E2, you see? E2 over here. So, partial E2 respect to X1 plus partial of A22 with respect to X2. You see, it's just this column over here. Plus, let's erase it here. Plus partial of A32 respect to X3. See? Now, see? E2. Let's put here plus E2. Plus, now, this last column here. Partial of A13 respect to X1 plus partial derivative, okay, P23 respect to X2 plus partial A33 X3, this is E3. So, this x1 component. This is x2 component. This is x3 component. So this is a vector. A vector. See? So gradient of v, okay? Now we are doing divergence. Gradient v is a second order tensor. Divergence of a second order tensor is a vector. Now, see? Okay, we know that divergence of second order tensor is a vector. We know this. The key is here. Now, by inspection, you see an interesting thing here. You see, look. You see, here is 1, 1, 1, and 1. You see? Now, I'll put this one over here. You see? Look at the blue one. Now, we see here, look, this is 2, 2, 2, and 2. This is 2. Now, here, 3, 3, 3, and 3. So I can write, okay, something like EI. You see? Because when I is equal 1, I'm here. When I is equal 2, I do this. I is equal 3, I do this. Now, how can I write the derivative? Okay, the partial derivative. You see, always you have, look, 1, 2, 3. See, look, 1, 2, 3. This, 1, 2, 3, in black, 1, 2, 3. So there's a sum over here, okay, which easily we can write down like this. Look, now come the partial derivative. This is A, this is x. Now you see, look, 1, 1, 2, 2, and 3, 3. Look, 1, 1, 2, 2, and 3, 3. So this is a sum, okay, a sum. So if I write down here J, I put J over here. And here will be I. You see? Now, look how interesting. Partial of AGI with respect to xj. Now, look, if you sum for j, you just have 1, 1, 2, 2, and 3, 3 is right there for each I, okay? Now this, as we know, the notation, we just forget the unit vector and then the components of divergence of A will be like this. Partial of A ji with respect to xj. See? Now look, if I exchange here, no problem. So I'll raise here. Yeah? Look, if I exchange there is no problem. I could write like this. So divergence of a second order tensor can be written as, for instance, partial of aij with respect to, look, you see this j here? I put I over here, xi, and this will be j, no problem. So I exchange j by I and I by j. So what is the free index in this case? So you see, what is important is the sum here, aj and xj. Look, ai, xi. You see, and j here is the free index. No problem. Here, I is a free index. No problem. I can write it like this. So, you see, if I develop this, okay, I be the dummy, I will reproduce all of this 9 terms over there. You see how easy and I would say fantastic is a tensor notation. They substitute, you see the whole terms that we are written over there. Also, you can write here as Aij dot I. See? Same. I is dummy, okay? Comma I means partial derivative of Aij respect to xi. See? It's a vector. It's a vector. Vector. This is a second order tensor. Let's write here. Second order tensor. Let us see the result of rotational gradient of a scalar. Rotation is the cross product of nabla across this vector. So rotation of a vector v, okay, remember this, okay, we can write epsilon I j k. Now the rotation of v, okay, forget gradient v. Let's put the v here. Don't forget, this is partial derivative of v and x. Do you remember? So k comes here, k comes here, and j comes here. Don't forget that. See, you can't forget this, okay? Otherwise, you will not reproduce what we developed. Now, you see, let's substitute. Now, Vk, look, Vk is, in this case, okay, I'll put the red here, just for you to see what we are doing. Vk. V is gradient phi, okay? V, let's write down gradient of phi is equal nabla phi, okay? V is this. I'll substitute nabla phi over here. So Vk is partial of phi respect to xk. See how easy this partial derivative respect to xk. You see? Now, what are the components of this vector? v1, v2, v3. What are the components of this vector? Partial phi respect to x1, or because it's free. Okay, this is free here. Free. I'm just looking at this. I'll substitute vk over there. So this will be epsilon I gk partial respect to xj. Now, look, this is equal partial of phi respect to xk. You see? Look here. This is vk. This is vk. This is vk. Now, this is a second derivative. So, this is equal epsilon I jk. Now, that's the second derivative of phi with respect to xj, xk. You see, that's the second derivative. Now you see an interesting point. Look, suppose you have a function phi like that, okay? I will write in the traditional letters, okay? x2, y, z5. Look, I'll get the derivative of phi with respect to x. Okay, this will be 2x, y, z, 5. Now, I will derive with respect to y partial of phi with respect to x, okay? Now I'll derive this with respect to y. This will be 2x z5. 2x z5. Now I will do first, let's erase here. Now I will do first derivative with respect to y here. Okay? Partial of phi with respect to y. This will be x2 z5. x2 z5, because x and z are constant, because this is a partial derivative. Now I'll do the derivative of phi with respect to y. Now I'll derive with respect to x. So it'll be 2x z5. Okay? Look here. If I exchange the order of the derivative, you see here? You see here? The function is the same. It's the same. Look, this is the same. I will exchange the order of the derivative here. I will exchange j and k here. So this will be epsilon. Now, it's not ijk. Now, ikj, because I will exchange j to k. So this is partial of phi with respect to k respect to j. This, look, this here, this derivative here, is the same as this one, like we did over here. Now, you see, because I move just once k here in the middle, you see, k here in the middle, this one is minus. So what you got here, we have gotten here, see, is this. Look, right here. Okay, suppose this is plus. Okay, so partial second derivative of xj xk is equal, suppose this is 1. Now, if this is 1, this is minus 1. If this is minus 1, this is 1, because I just moved once, is equal minus partial of phi respect to xk respect to xj. You see, 1. This implies that partial derivative of phi respect to xj xk must be 0. You see, look. A number 8 is equal minus 8. Suppose this is 8, this is minus 8. A number cannot be equal, it's symmetric. So only if this is 0, if it's 0. So rotational of a gradient, look, rotational of a gradient, a function is equal vector 0. It's proved. That's easy from here. Imagine if you develop this without using tensor notation. Okay? You'll be many terms just for you to prove this. Okay. This again, just a brief review. Okay? This is divergence of a second order tensor is a first order tensor, is a vector. See? J is free index. Now, you see, I will emphasize an observation over here that you could see in the little confusion, okay? But I will clarify for you. Now, look, you see gradient of something, okay? This could be a scalar, a vector, a second order tensor, a third order tensor, doesn't matter. A gradient of something operates here. You see, you put here, for instance, partial of what's coming here, what I put here, xi, this comma xi. So you know before doing anything that this is a second order tensor. So v is a vector. So suppose you do this. Nabla v, okay, you put it here, partial xi. Suppose you put vi here, okay? Because you see I over here, it's this I over here. Now, you can't do that because if you do that, I is dummy. So you have to change or put k or put j or put other thing here. See, that's why a gradient of a vector, you have to have two free indices. You have to have. See, you can put j. Also, if you want, you put j over here, but here you cannot put j. You put I. No problem. Okay? That's why I wrote right here. See, it's important because you know gradient, okay, of something that comes here, comma I. If you put a vector here whose index is I, it's wrong. It cannot be I or JJ. See, that's an important observation for you. Suppose you want this dot product here. V dot nabla V. See? V dot nabla V. You can do this. You have two options to do that. Or you do this, or you do this. V dot nabla apply to V. See? Or you do this way, or you do this. You'll be the same. Let's write down this over here. You see, look. What is this? This is scalar. Okay? Now, if I introduce here a vector, so this whole term will be a vector. Because this is scalar. If this applies to a second order tensor, because this is a scalar, this will be a second order tensor. How can I write a dot product between two vectors? What are they? V and the pseudo vector. This is a pseudo vector. Okay? This here is a pseudo vector. This is there. Okay, look, a pseudo vector. So this dot product yields this. Now I'm looking at this term here. Let's write down V over there. V or other vector. Or a scalar. Now, suppose I put a scalar here, so this is scalar there. So the whole term will be a scalar. Suppose I put a vector right here. This will be just VI. So this is VI. See? Has to be I. Cannot be J. Okay? Because J is dummy. So I put I. So this represents this term over here. Now, look. I will develop this over here. Okay? Now, V dot nabla V. Okay, nabla V this is, I'll put here partial of VI with respect to xj. This is nabla V right here. Now, you see, you look at here, this has to be Vj. Okay? Because Vj sum, you have here J is dummy. And I is free. I is free. I. You see, this is identical to that. Okay? I have to. Now, one more observation. Look, since nabla is a pseudovector, v dot nabla is this is completely different of nabla dot v. Completely different, because this is an operator and this is divergence, this is a scalar. Don't confuse, see, because sometimes you confuse. When you have a dot product A dot B, this is equal B dot A. Why? Because it's the magnitude of A, magnitude of B, cosine of the angle between A and B. But this does not, it is not valid for this one. Okay, V dot nabla, you see, V dot nabla is operator. Okay, nabla dot V is the divergence. This is divergence. This is not divergence. Be careful on this. Okay? This is a very, very important operator. I can write this operator like this: Vj partial of xj. You see, suppose instead of V, suppose this is a scalar, like temperature. Okay? Temperature change with the point, x, y, z. Now, V dot nabla applied, for instance, in the temperature. Okay? Now, you see, look at here. I can also split in two options. It will be the same. Here will be V dot nabla t, or V dot nabla operator on t. The same thing. See? Now, what is the result of V dot nabla t? T is a scalar. Gradient of a scalar is a vector. A dot product between two vectors, this is a scalar. It's different from here, because here is a vector. You see, look, this is a second order tensor, this is a vector. A dot product between first order tensor and second order tensor will be one order tensor, a vector, like here. Now, you see, V dot nabla, this is a scalar, applied to a scalar, so this is a scalar. Okay, the same thing. Doesn't matter if you apply here or there, use, instead of use this or that, that's the same. Okay? Could be also a second order tensor. Instead of V, instead of T. V dot nabla, this is called, in thermal science, that is called transport operator.